Hey everyone, this is a video lesson that I'm using in my AP Calculus AB class, and I'm putting it online in case it would be helpful to others as well. There is a link to a printable set of guided notes in the description of this video that you can use to follow along with the examples that I do in the lesson. In this section, we are going to look at one of the most revered things that students learn in a Calculus 1 class, and that is LHopitals Rule. LHopitals Rule is a new and different way to evaluate limits. And I don't want to give too much away, but I'll tell you, it combines evaluating limits with derivatives. So really exciting stuff, right? Since L'Hopital's rule is a way for evaluating limits, the first part of this lesson is just reviewing exact ways that we can use to evaluate limits. You've already learned a few of those methods, so I want to review them before we discuss what L'Hopital's rule says. There were quite a few ways to evaluate limits in the first unit of our course. However, there were three in particular that were exact methods for finding limits. I'm wondering if you remember what the first one is. What is the first thing you should always try when evaluating a limit? You might have to think way back to figure that out, right? Okay, I'll tell you, it is substitution. Right? Substitution is the first thing you should always try, and if it works, you're done. If it doesn't work, that tells you actually, what route you should take to continue, because you will either have something that is undefined or you will have something that is an indeterminate form. If you have something that's an indeterminate form, there are two other exact methods that we looked at for determining the limit. One of them was called manipulation. That is where you use, algebra or trig identities to rewrite the expression that is in the limit so that you can then go back to trying substitution. The third method that is an exact method for finding limits was the sandwich theorem. Remember that? Or squeeze theorem, which I thought was pretty fun. I don't know if you agree, but that is the other exact method that we discussed. So what I'm going to encourage you to do right now with the first set of exercises is try any of those three methods on the limits that you see here. Okay, for example, I'll give you a hint. In number one, you could use factoring, right? In number two, you could rewrite tangent in terms of sine and cosine. And the list goes on and on of super fun things that you can do. Now, don't be too discouraged if you cannot answer all of these limit problems. I want you to try as many as you can. And then I'm going to swoop in and save your day by showing you how you can evaluate them with L'Hopital's rule. I'm going to pause the video and write some solutions in. I suggest that you pause the video now too and try these. And I'm back. I have answers filled in to the first 6 limits, and I'll talk you through them right now, but I also think if you need to, you should pause the video so that you can copy down the work if you were not able to complete the limit on your own. Okay, so as I said, number one, we could complete by factoring and then dividing out the common factors of x minus 4. However, I want to make sure that I mention that for each of these methods, the first thing that you should try, each of these limits, the first thing that you should try is substitution to see what happens. If you can use substitution to evaluate the limit, that is what you should use. You should also try substitution to ensure that you have an indeterminate form before trying another method for evaluating. So in number one, I did show that I tried to substitute x equals 4 into the expression x squared minus 16 over x minus 4, and I got 0 over 0. And so then I proceeded to my factoring and dividing out common factors to rewrite the expression as x plus 4. I can then sub the 4 in for the x to find that my limit is equal to 4 plus 4, which is 8. In number one, again, I checked for substitution first. I found the indeterminate form, and then I went about manipulating tangent x over x by rewriting tangent as sine over cosine. Tangent x is sine x over cosine x. I split apart this fraction then into sine x over x times 1 over cosine x. You know, we have two denominators here. We have a cosine x in the denominator and an x in the denominator. You are allowed to rewrite those denominators in this form so that then you can evaluate the limit as x approaches 0 of each of those pieces separately. So we know that the limit as x approaches 0 of sine x over x is equal to 1. We proved that back in the first unit of this course, and we use that limit a lot throughout the course. And for this limit, the limit as x approaches 0 of 1 over cosine x, we can substitute 0 in for cosine because cosine of 0 is 1. And so that leaves us with a limit answer of 1. Okay, now the real fun begins. Take a look at 3 and 4. Notice that with 3, I did check for substitution first, and I found that as I subbed in -2 for all of my x's, I came to a 0 over 0 situation. And so that told me that I need to move on to try some sort of manipulation technique. And I'll tell you what I did next was I realized that this denominator could easily be factored because it is a quadratic. And I could figure out factors of -10 that had a sum of -3 pretty easily. Those factors are x minus 5 and x plus 2. And because I'm doing the limit as x approaches -2, I kind of knew that there was going to be a factor of x plus 2 in my numerator as well. And so I did one of my favorite things over here. It's not actually one of my favorite things, but I did it because I knew I had to. I did synthetic division of x cubed plus 4x squared plus x minus 6 by x plus 2. You can see my work for that over here. To find that the other factor that I needed in my numerator was x squared plus 2x minus 3. Okay, so it was a bunch of factoring, but to help me factor the numerator, I had to use some synthetic division. I then divided out the common factors of x plus 2, and I could sub -2 in to all of the x's that remained to get a limit value of 3/7. In number 4, we could use a fun technique called multiplying by the conjugate, right? Does that seem familiar? Where in the numerator of this expression, we had the square root of x plus 2 minus 3. Its conjugate would be the square root of x plus 2 plus 3. And if I multiply the numerator and denominator by that conjugate, I'm not changing the expression because I'm really multiplying by 1. And so that's why I'm allowed to do that. Whenever I distribute these two binomials in the numerator, I get x plus 2 minus 9. Notice that I did not distribute in the denominator because I realized that x plus 2 minus 9 was going to combine to x minus 7, and that could divide out with the factor of x minus 7 in the denominator. That leaves me with 1 over the square root of x plus 2 plus 3, and I could sub 7 in for the x that remained to get a limit answer of 1/6. So much fun, right? Finally, I realized that at some point I did forget to show that I was trying substitution for all of these, but let's just go with it. You can definitely tell that I tried substitution here, the easiest one of them all. But before we get there, let's talk about number 5. What did I use for number 5? Can you tell? For this one, I used the sandwich theorem or the squeeze theorem. I saw that I had a sine of 5 over x in my expression, and I knew that I could sandwich that between -1 and 1, right? And from there, I multiplied all pieces of this compound inequality by x, which then allowed me to take the limit of each extreme here, the limit as x approaches 0 of -x equals 0, the limit as x approaches 0 of x equals 0, and since these match, I can say that means that the limit as x approaches 0 of x sine 5 over x equals 0. We might as well finish that statement with by the sandwich theorem. And finally, for number 6, what did I use here? I used direct substitution. I subbed 0 in for the x, and that worked. 7 times 0 is 0. Cosine of 0 is 1. I have a 7 in the denominator, therefore my answer is 1/7. No need to do any other methods with number 6. Okay, so that was a lot of work, and all of that was to review all of the different things that we've talked about with evaluating limits to get an exact answer. Keep in mind, you can always approximate a limit answer using numerical approximation or graphical analysis, but I wanted to review these manipulation techniques slash substitution slash sandwich theorem to show you that we had all of these options available to us. But some of them were pretty long and a little bit difficult. But now we have something called L'Hopital's Rule. And what I want to now talk to you about is how this can come in and save the day and help us get our answers to our limits that have indeterminate forms much easier. So in the wording that we have here for L'Hopital's Rule, what we are seeing is that the function of f at a and the function g at a both result in 0, which would give our limit here a 0 over 0 indeterminate form. If that's the case, and we have the derivative of f at a and the derivative of g of a existing, and g prime of a not equal to 0, then we can evaluate the limit as x approaches a of f of x over g of x by evaluating the derivatives of the functions at x equals a. I don't know if that makes a whole lot of sense to you right now, but I promise you when you see some examples of that, you're going to say, oh, wow, that makes things a lot easier. Before I show you those examples, though, I do want to do a little proof with you about L'Hopital's Rule and why it works. This is where I do need to refer to my answer key because I am not always super confident when I do these proofs. Okay, if we're going to use something as special as L'Hopital's Rule, we want to make sure to prove it ahead of time. You're not going to have to prove L'Hopital's Rule for yourself at any point in this class, but I still want to go over it with you because I think it's really important. Okay, first of all, we're going to use something called the method of backwards induction for this proof. This is not the only way to prove L'Hopital's Rule, but it's one that I thought was the easiest to understand. What that means is we are actually going to start with the result, the f prime of a over g prime of a, and we are going to manipulate that to hopefully get to this point where we can write the limit as x approaches a of f of x over g of x is the same thing. Okay, so again, let's start with f prime of a over g prime of a. And from there, we can rewrite f prime of a and g prime of a in terms of the definition of derivatives. This is a derivative of f at x equals a, right? Well, that can be defined as the limit as x approaches a of f of x minus f of a over x minus a. That we called in this class the alternate definition of derivative. Does that sound familiar? I hope so. For g prime of a, we can do the same thing. We can rewrite it as the limit as x approaches a of g of x minus g of a all over x minus a, again, by the alternate definition. From there, we are going to pull this limit out, these limits, I should say. Because they are both the limits as x approaches a, we can apply that limit to this entire complex fraction. And from there, I'll do one more little maneuver here that might help you understand why this happens. If you have a fraction divided by a fraction, you could rewrite that as the top fraction times the reciprocal of the bottom fraction. And here I hope you can see that the x minus a's are going to divide out to 1, right? And so what we are left with is the limit as x approaches a of f of x minus f of a over g of x minus g of a. Finally, keep in mind that f of a and g of a, they are 0, right? We assumed that right here. And so we can say that if f of a and g of a are 0, then what we have here is really the limit as x approaches a of f of x over g of x. I don't know why I really put a box around that. It's not an answer. There's all sorts of ways that we can show that we've done the proof. We could write QED, but what we just did here was we took the f prime of a over g prime of a. We manipulated it to show that if we have f of a and g of a equal to 0, or in other words, 0 over 0 for this limit, then these are the same thing. And that is proving that we can use this little rule called LHopitals Rule to evaluate limits of an indeterminate form of 0 over 0. Okay, so now that we've proved it, let's use it. Now, I want to warn you, LHopitals Rule can only be used for limits of indeterminate forms, and really, we only proved in the proof that we did that it can be used for an indeterminate form of 0 over 0. So please make sure to check for that indeterminate form before applying this rule. Okay, now the fun begins. Let's evaluate each of the limits that we already did in our warm-up. Try these exercises, but now for most of them, we will use LHopitals Rule. I have to warn you, not all of them though. Okay, for number 1, again, I want to remind you that the first thing that we did was we checked for the indeterminate form 0 over 0 with substitution. And I'm kind of squeezing in all of my work here, so I'm not going to write that out, but what I'm doing here in my brain is I'm thinking 4 squared minus 16 is 16 minus 16, which is a 0 in the numerator, and 4 minus 4 gives me a 0 in the denominator as well. So I have that 0 over 0 indeterminate form, which means I can apply LHopitals Rule in this situation. And so here's how we apply it. Ready? We are going to keep the limit the same. It will still be the limit as x approaches 4, but we are going to change the expression to the derivative of the numerator over the derivative of the denominator. Take the derivative of x squared minus 16. That's just 2x, right? Take the derivative of x minus 4. That's just 1. Use this expression with substitution to get your answer. Remember that was the answer to number 1? Look, I'll go back. The answer was 8. We got that answer using factoring and dividing out common factors and then substitution. But here we got it a little bit easier, I'd say, using LHopitals Rule. Let's try another one. I'm kind of mixing up my colors here. I'm sorry. Okay, again, whenever we used substitution, we did get 0 over 0. And so we know that we can definitely apply L'Hopital's rule. Keep the limit the same. Take the derivative of the numerator. The derivative of tangent x is secant squared of x. Take the derivative of the denominator. The derivative of x is 1. And substitute 0 in for x. What do you get from that? Well, okay, secant is 1 over cosine, right? So 1 over cosine of 0 is 1. 1 squared is still 1. That was the answer to number 2 that we got earlier, right? But this time we got it using L'Hopital's rule. Okay, I think you're definitely going to see how helpful this rule can be with number 3. Remember, number 3 was the one where we had to use synthetic division. We had to factor, we had to use synthetic division, then we had to divide out, then we had to finally sub in -2 again. Quick reminder though, when we sub in -2 at the start, we did get 0 over 0. And so we can use L'Hopital's rule here, which says keep the limit as x approaches -2. But let's do the derivative of the numerator. That derivative is 3x squared plus 8x plus 1. Take the derivative of the denominator. That is 2x minus 3. Now sub in -2 for all of our x's. And let's see what we get from that. You might want to use a calculator for this. This is a -2, by the way. I know it looks weird. Sorry. Okay, what do we get from this? We have a 4 here times 3 is 12. We have -16. 12 minus 16 is -4. Plus 1 is -3. Here we have -4 minus 3, which is -7, and -3 over -7 gives us an answer of 3/7. And you can look back if you want to. I will too, but I'm pretty sure, yep, that is the answer that we got for number 3 the first time. With all that crazy work, now, like this. Let's do another one. Okay, for number 4, this is the one where we used the technique of multiplying by the conjugate originally. But since we would get a 0 over 0 situation when we use substitution, that means that we can use L'Hopital's rule. Okay, keep in mind that the square root of x plus 2 could be rewritten as x plus 2 to the 1/2 power. And so to do L'Hopital's rule, we need to use the power rule. The 1/2 would come down in front of the x plus 2, and we would get a -1/2 power. Oh, that looks a little bit weird. Let me fix that. The derivative of the -3 goes to 0. And in the denominator, you don't really need to write that if you want to, because what's the derivative of the denominator? It's 1, right? Just like this one was 1. We didn't really need to write it. The derivative of x minus 7 is 1. And so now we can use this expression to evaluate our limit by subbing 7 in for x. And let's see, 7 plus 2 is 9. 9 to the -1/2 power, what's that? That is 1/3, right? 9 to the 1/2 power is 3. 9 to the -1/2 power is 1/3. Multiply the 1/2 with the 1/3, and we get that answer we were looking for, which is 1/6. Okay, finally, for the last two, these are examples that actually you cannot use L'Hopital's rule for, and so I'm not going to write out all of the work again because we already do know the answers, but I would like to know why we can't use L'Hopital's rule. When we use substitution for number 5, we get 0 times sine of 5 over 0, And that is not an indeterminate form where L'Hopital's rule can be applied. This is something that we should recognize as an indeterminate form that we will need to use sandwich theorem for, or squeeze theorem. Finally, number 6, keep in mind that's one where we don't need any special technique to evaluate, because when we use substitution, it works. Cosine of 7 times 0 over 7 is equal to 1/7. Not an indeterminate form. We get an answer right away, so we know we're done. So going back to this warning, I'm calling it a warning because sometimes we just get into a groove of using L'Hopital's rule for every single limit that we see, and in some cases that could be detrimental, and number 6 is one of them. If you try to take a derivative here, you're going to get -7 sine of 7x over 0, and that's not going to work, right? And that's not needed anyway. So do check for indeterminate form that L'Hopital's rule can be used on. And so far, we've established that it can be used for 0 over 0 indeterminate forms, not a form that looks like this, which is characteristic of sandwich theorem, and not one where you could just use direct substitution. Okay, so now let's talk about some other indeterminate forms where L'Hopital's rule can be used. So indeterminate forms, or the indeterminate form that we've discussed so far and that our L'Hopital's rule was proved with, is 0 over 0. Okay, there are other ones, however, and I do want to address them, even though we're not going to prove that L'Hopital's rule could be used with them. I will mention that if you have positive or negative infinity over infinity, that is a time where you could use L'Hopital's rule. These are the most common ones, by the way. I will show you an example of this one. However, there are some others that we don't really talk about very much, at least in this class, but they are out there, so I will mention them. One of them is infinity times 0. One of them is infinity minus infinity. One of them is 1 to the infinity, 0 to the 0, and the last one is infinity to the 0. Again, this is a lot more than we are going to cover in this notes, but I kind of like to have a complete set of all of the indeterminate forms where L'Hopital's rule can be used, even if we won't see examples of all of them here. Okay, so next I want to remind you of something that will be helpful for the next example. Please recall that the limit as x approaches 0 of 1 over x is undefined, or this limit does not exist, right? But when we dig a little bit deeper, like let's start by substituting 0 in for x, we see that we get 1 over 0. And this is a case where we have likely a vertical asymptote going on. I had to think really hard about how to spell that. I think I got it. Which means that this is actually a limit that results in infinity or negative infinity. If we take the limit as x approaches 0 from the left of 1 over x, we would have 1 divided by a very small number that's close to 0 but negative. So therefore, we would say that that goes to negative infinity. And if we look at the other side, the limit as x approaches 0 from the right of 1 over x, that's going to be 1 divided by a very small number close to 0 but positive, and so therefore we'd say it's going to positive infinity. Knowing those will be helpful for the next example. In example 2a, we are going to find the limit as x approaches 0 from the right of sine of x over x squared. And I'm going to show you why you can use L'Hopital's rule here. First, why you can use L'Hopital's rule, and then how you can use it. So first, the why. Let's use substitution. And what we are doing here is subbing in 0 for x, and we are getting 0 over 0, our indeterminate form that we definitely know because we proved that L'Hopital's rule could be used in. Okay, so now we are going to rewrite this as the limit as x approaches 0 from the right of the derivative of sine of x, which is cosine of x, over the derivative of x squared, which is 2x. Now let's try substitution again. Subbing 0 in for the cosine results in a 1, right? Subbing 0 into the denominator for the 2x results in a 0. So we get 1 over 0, which indicates to us that this is, again, probably going to be an answer that is infinite. Since we are approaching 0 from the right, which means here we would have something really close to 0, but not actually exactly 0, but positive, we can therefore say that this is going to infinity, just like we said with this one. In this other case, you're going to end up with the same 0 over 0 situation when you sub. Let me write that as x first. We again have 1 over 0. Cosine of 0 is 1. 2 times 0 is 0. However, this is very close to 0 on the negative side because we are approaching from the left, and therefore we can say that goes to negative infinity. So L'Hopital's rule can work with infinite limits as well, limits where our answer results in infinity, as long as your initial try with substitution results in one of these indeterminate forms. Next, let's look at one where actually when we try substitution, we're not going to get that 0 over 0 form. We're going to get one of the other indeterminate forms. Let's try substitution with the limit as x approaches pi over 2 of secant x over 1 plus tangent x. That gives us secant of pi over 2 over 1 plus tangent of pi over 2. Okay, well, what is that? Just in the interest of time, I am going to bring up my calculator here to show that secant of pi over 2, let's see. Sorry, I forgot what I was doing for a moment. I should say at pi over 2 for secant, it is an asymptote, okay? Which means that coming from one side, we're going to positive infinity. Coming from the other side, we're going to negative infinity. In this case, it's from the left, we're going to negative infinity. From the right, we're going to positive infinity. I'm just going to call that plus or minus infinity here. And when we graph 1 plus tangent of x, looking at pi over 2, we again see an asymptote where from one side we're going to positive infinity, from the other side we're going to negative infinity. So again, I can say that this results in plus or minus infinity as well. I mean, really, you might want to split it up and say from the right, it is positive infinity over positive infinity. I'm sorry, from the left, it's positive infinity over positive infinity. From the right, it's negative infinity over negative infinity. But I'm just going to put it together like that. And that was really just basically to show that I have one of those indeterminate forms that we listed up here where I can use L'Hopital's rule. So that's the exciting part of all of this. To figure out this limit, we can just take the derivative of the numerator. The derivative of secant of x is secant of x tangent of x over the derivative of the denominator. The derivative of 1 is 0. The derivative tangent of x is secant squared of x. And we can try to simplify that. Okay, so what's going on here? This can divide out with one of these, right? And we have tangent x. Oh, this is where, oops, I forgot to write my limit. This is where I'm just getting so excited because I'm like, yes, I can do some trig manipulation here now. Over secant of x. And that is the same as sine of x. Did you know that? Tangent is, if you want to write it out, sine x over tangent x is sine x over cosine x. Secant x is 1 over cosine x. I'm not going to do the reciprocal step here. I'm just going to say those divide out, right? Oh, I forgot to write my limit again. Let's just put it up here. So what we now are evaluating is the limit as x approaches pi over 2 of sine of x. Look at this. I'm getting so excited, like my writing's getting crazy. And we can use substitution here because sine of pi over 2, that's not an indeterminate form or undefined, nothing crazy going on there. That's just 1. So there's our answer to our limit. So we started with trying substitution and seeing that we have a positive or negative infinity in the numerator and the denominator. But when we applied L'Hopital's rule, we found that we got a limit answer of just 1. Okay, here's one more where we are going to see infinity over infinity when we use substitution. So in this one, we're going to, okay, this is where I'm going to do something that is not technically allowed, but I do it anyway because I think it's helpful. Can we really use substitution here? Not really, but I'm going to go for it, and I'm going to say we're subbing infinity in here and infinity in here. I know, you're not really allowed to do that, but we're going for it anyway. Okay, and what we're really just trying to think about in this case is as x gets bigger and bigger and bigger, what happens to the value of the natural log of x? Okay, well, I mean, if you want to look at it graphically, we could just to save some time. As x gets larger and larger and larger, so does the natural log. Okay, there is no horizontal asymptote limiting the natural log value. I mean, it does not get bigger and bigger and bigger very quickly, but there is nothing limiting this value to a certain number. It does keep increasing as you make x larger and larger and larger. So we will call it infinity. What happens with 2 times root infinity? Okay, well, again, what you're really asking there is as x gets bigger and bigger and bigger, what happens to the value of 2 root x? And again, this is a case where, well, it doesn't go really quickly again, but as you move along to the right, or as you make that x bigger and bigger and bigger, your y is also getting bigger and bigger and bigger, increasing, and so we will call that again infinity. So here again is an example of an indeterminate form infinity over infinity where we can use L'Hopital's rule. So again, what we're going to do is keep the limit, take the derivative of the numerator, that's 1 over x, take the derivative of the denominator. Keep in mind, 2 root x is the same as 2x to the 1/2 power. So the 1/2 comes down and multiplies with 2, making a coefficient of 1. Take 1 away from your power, making it a negative 1/2 power. We could rewrite this as the limit as x approaches infinity of, okay, 1 over x is like x to the negative 1, right? And if we have a negative power in the numerator, negative power in the denominator, we could just switch those around like that. But also, now that we see it like this, we could say, well, let's subtract the powers of our x to get 1 power on the x. So I'm just simplifying. Or I could rewrite that. I know I'm putting like equal signs with nothing on one end. I'm sorry. Should erase those. I'm just worried about my spacing. 1 over root x. X to the negative 1/2 is 1 over root x. Now, subbing infinity into this, what do we get? We get 1 divided by something that's getting larger and larger and larger. So what's that going to go to? Anytime you have that situation, it goes to 0. Okay, so this is where usually when I'm in a class, I have students who say, okay, at this point they say, if you have infinity over infinity in your indeterminate form, isn't that always just going to result in 1? And I say, no, in this case it did. However, look at this example. We had infinity over infinity, yet it resulted in 0. Okay, I could talk a whole lot with you about relative magnitude and why these things happen. I'm trying not to make this video forever long though, so we'll save that discussion for another time. Okay, finally, additional notes and examples. This note says that L'Hopital's rule can be applied more than once to evaluate a limit, and you're going to see an example of that here in example 5. Let me show you what I mean. What we have here is the limit as x approaches infinity of e to the x minus 1 over x squared. And when I try substitution, I get, again, this is like one of those things you shouldn't really write, but I'm going to write it. I get e to the infinity minus 1 over infinity squared, which is definitely going to result in infinity over infinity, because an exponential going to infinity definitely goes to infinity. Infinity squared definitely goes to infinity. So let's apply L'Hopital's rule, where I will rewrite this as the limit as x approaches infinity of the derivative of the numerator, which is e to the x, over the derivative of the denominator, which is 2x. Now, when I try substitution again here, I get infinity, e to the infinity over 2 times infinity. Again, this is like poor notation, but I think it works for what we need to do. That again results in infinity over infinity. E to the infinity is infinite. 2 times infinity is infinite. So what do we do with that? We do L'Hopital's rule again. See if it works after a second time. Take the derivative of e to the x. That is just e to the x again. The derivative of 2x, however, is just 2. And so now when we try substitution again a third time, we get e to the infinity in the numerator over 2. What does that result in? That does not result in an indeterminate form. That results in an infinite amount, an infinite whatever in the numerator, infinity in the numerator, I should have said, and 2 in the denominator. Infinity divided by 2 is infinity. And so that is our answer to example 5. Okay, this one is not going to result in infinity. You won't have as many infinities involved there, but I would encourage you to try it now. Anytime you're making a polynomial go to infinity, that answer is infinity. So here we would have infinity over infinity when you try substitution initially. So what I recommend now is you pause the video, you try to apply L'Hopital's rule, think about what happens, and I'll give you a hint, you're going to have to do it more than once. Okay, I came back with an answer of 3. Is that what you got for the limit? When you apply L'Hopital's rule once, you get 18x minus 5 over 6x, but subbing infinity in for these x's will result in infinity over infinity again. And so therefore, we try to apply L'Hopital's rule a second time, and what we end up with is 18 over 6, and that limit is equal to 3. Now, I would like to note that, I think that just thinking about end behavior might be a simpler route to take here. So L'Hopital's rule isn't always the one way that you should go that's going to be the easiest way. We could say that because we're going to infinity, we could take the term of the highest power in the numerator over the term of the highest power in the denominator and simplify, and we would get that answer of 3 right away. But again, L'Hopital's rule can be applied to something like this because we had that infinity over infinity indeterminate form. Okay, finally, every year that I teach this, I think to myself, okay, I'm really afraid that now that my students know this, they're just going to always do derivative over derivative when they see a rational function. So take a look at example 6 and read this warning with me. The warning says you differentiate the numerator and denominator separately only when using L'Hopital's rule to evaluate a limit. Okay, quotient rule is still a thing. Sometimes I have students think, so we don't have to do quotient rule anymore, right? No, that's still a thing. That's a thing that you do when you're taking the derivative of a rational function. L'Hopital's rule, which is derivative over derivative, is a thing that you do when evaluating a limit of an indeterminate form where it works. All right, so let's try to make that distinction here in example 6. We have the function x squared minus 9 over x squared minus 3x, and in part A, we are asked to evaluate the limit as x approaches 3 of f of x. Okay, so we're doing really here the limit as x approaches 3 of this function. Let's just write it as the function expression instead of f of x. And then let's try substitution. And we get 3 squared minus 9 over 3 squared minus 3 times 3, which is 0 over 0. So applying L'Hopital's rule, which is, again, where we can do derivative over derivative, we get 2x over 2x minus 3, and subbing 3 in for x again, we get a limit answer of, 6 over 3, which is 2. There's our answer. Okay, so again, that is where you can just take the derivative of the numerator over the derivative of the denominator. We did that because we were evaluating the limit with L'Hopital's rule. Okay, however, take a look at B. It says find f prime at 1. Okay, in this case, we need to use quotient rule. We are not evaluating a limit, so L'Hopital's rule is not a thing here. We have to get f prime of x with low d high minus high d low all over low low, and away we go with subbing 1 in for all of those x's. Or you might want to simplify that a little bit. One more time, I suggest you pause the video, maybe try to simplify your f prime of x equation, and then sub 1 in for the x to get the answer to that derivative. And I paused the video as well. I left out some steps because I was running out of room, but I simplified my f prime of x function to negative 3x squared plus 18x minus 27 over x squared minus 3x quantity squared. I subbed 1 in for all of the x's to find my derivative value at x equals 1 to be negative 3, or in other words, that is the slope of this function at x equals 1. Okay, so again, quotient rule is not out. L'Hopital's rule is something completely different that uses derivatives but within limits. Okay, as usual, I hope this video was helpful. Bye.